Section 4.2, Multiplying Fractions. In this video we will see the multiplication rule for fractions and how to create a visual argument for multiplying fractions, how to multiply fractions with the multiplication rule, how to multiply and reduce, how to multiply and cancel or cancel and multiply, the cancellation rule for multiplying fractions, what to do when everything cancels, how to find the area of a parallelogram and a triangle, and how to identify the base and altitude of different triangles. Consider the image in figure 4.5, where the vertical lines divide the rectangular region into three equal pieces. If we shade one of the three equal pieces, the shaded area represents 1/3 of the whole rectangular region. We'd like to visualize taking 1/2 of 1/3. To do that, we draw an additional horizontal line which divides the shaded region into half horizontally. This is shown in figure 4.6. The shaded region that represents 1/3 is now divided into two smaller rectangular regions, one of which is shaded with a different color. This region represents 1/2 or 1/3. Next, extend the horizontal line the full width of the rectangular region as shown in figure 4.7. Note that drawing the horizontal line coupled with the three original vertical lines has succeeded in dividing the full rectangular region into 6 smaller but equal pieces, only one of which, the one representing half of 1/3, is shaded in a new color. Hence, this newly shaded piece represents 1/6 of the whole region. The conclusion of our visual argument is the fact that 1/2 of 1/3 equals 1/6. Example 1. Create a visual argument showing that 1/3 of 2/5 is 2/15. Solution. First, divide a rectangular region into 5 equal pieces and shade 2 of them. This represents the fraction 2/5. Next, draw 2 horizontal lines that divide the shaded region into 3 equal pieces and shade one of the 3 equal pieces. This represents taking 1/3 of 2/5. Next, extend the horizontal lines the full width of the region and return the original vertical line from the first image. Note that the 3 horizontal lines coupled with the 5 original vertical lines have succeeded in dividing the whole region into 15 smaller but equal pieces, only 2 of which, the ones representing 1/3 of 2/5, are shaded in the new color. Hence, this newly shaded piece represents 2/15 of the whole region. The conclusion of this visual argument is the fact that 1/3 of 2/5 equals 2/15. Multiplication rule. In figure 4.7, we saw that 1/2 of 1/3 equals 1/6. Note what happens when we multiply the numerators and multiply the denominators of the fractions 1/2 and 1/3. The numerators multiplied is 1 times 1 is 1, and denominators multiplied is 2 times 3, which is 6. We get 1/6. Could this be coincidence or luck? Let's try that again with the fractions from example 1, where we saw that 1/3 of 2/5 equals 2/15. Again, multiply the numerators and denominators of 1/3 and 2/5. Numerators 1 times 2 is 2, and denominators 3 times 5 is 15. Again, we get 2/15. These two examples motivate the following definition. Multiplication rule. To find the product of the fractions a over b and c over d, multiply their numerators and denominators. In symbols, a over b times c over d equals a times c over b times d. Example 2. Multiply 1/5 and 7/9. Solution. Multiply numerators and multiply denominators. Multiplying the numerators together, we get 1 times 7 is 7. Multiplying the denominators, we get 5 times 9 is 45. So our answer is 7 over 45. Example 3. Find the product of -2/3 and 7/9. Solution. The usual rules of signs apply to products. Unlike signs yield a negative result. Multiplying the numerators, 2 times 7 is 14. Multiplying the denominators, 3 times 9 is 27. Since one of the fractions is negative and the other is positive, the result is -14 over 27. It is not required that you physically show the middle step. If you want to do that mentally, then you can simply write -2 over thirds times 7 over ninths equals -14 over 27. Multiply and reduce. After multiplying two fractions, make sure your answer is reduced to lowest terms. See section 4.1. Example 4. Multiply 3 over 4 times 8 over 9. Solution. After multiplying, divide numerator and denominator by the greatest common divisor of the numerator and denominator. So we have numerators multiplied together to get 3 times 8 equals 24, and denominators multiplied together is 4 times 9 equals 36. So we have 24 over 36. Now we will reduce to lowest terms by dividing both numerator and denominator by the greatest common denominator, which in this case is 12. In the numerator, 24 divided by 12 is 2, and in the denominator, 36 divided by 12 is 3. So the result is 2 over 3. Alternatively, after multiplying, you can prime factor both numerator and denominator, then cancel common factors. Once we multiply, we get 24 over 36. The prime factors of 24 are 2, 2, 2, and 3. And the prime factors of 36 are 2 times 2 times 3 times 3. The numerator and denominators have 2 2's in common and a 3 in common, so we will cancel all these and we're left with just a 2 in the numerator and a 3 in the denominator. The same result. Example 5. Multiply negative 7x over 2 and 5 over 14x squared. Solution: after multiplying prime factor both numerator and denominator, then cancel common factors. Note that unlike signs yields a negative product, so we can just focus on multiplying the two fractions and make the result negative. Multiplying the numerators, we have 7x times 5 is 35x, and the denominators, 2 times 14x squared is 28x squared. 35x factors into 5 times 7 times x, and 28x squared factors into 2 times 7 times x times x. They both have a 7 and x in common, so we're left in the numerator with a 5 and in the denominator 2 times x. Simplifying this, we get 5 over 4x. The result is negative 5 over 4x. Multiply and cancel, or cancel and multiply. When you're working with larger numbers, it becomes a bit harder to multiply, factor, and cancel. Consider the following argument. Multiply 18 and 35 to get 630 in the numerator, and 30 times 6 in the denominator to get 180. Finding the prime factors of these large numbers, in the numerator we have 2 times 3 times 3 times 5 times 7. In the denominator we have 2 times 2 times 3 times 3 times 5. Canceling what's common, we're left with 7 in the numerator, 2 in the denominator. There are a number of difficulties with this approach. First, you have to multiply large numbers, and secondly, you have to prime factor the even larger results. One possible workaround is to not bother multiplying numerators and denominators, leaving them in factored terms, and then finding the prime factorization of these smaller factors is easier. The prime factors of 18 is 2 times 3 times 3. The prime factors of 35 is 5 times 7. The prime factors of 30 is 2 times 3 times 5. And the prime factors of 6 are 2 and 3. Parentheses are no longer needed in the numerator and denominator because both contain a product of prime factors, so order and grouping do not matter. Now we'll cancel what's in common, and we're left with 7 in the numerator and 2 in the denominator. Another approach is to factor numerators and denominators in place, cross-cancel all that's common, so when we multiply, we just get 7 over 2. Cancellation rule. When multiplying fractions, cancel common factors according to the following rule. Cancel a factor in a numerator for an identical factor in a denominator. Example 6. Find the product of 4 over 15 and 30 over 140. Solution. First, multiply numerators and denominators to get 14 times 30 over 15 times 140. Then, find the prime factors of the numerators and denominators. So in the numerator, we have 2 times 7 times 2 times 3 times 5. And in the denominators, we get 3 times 5 times 2 times 2 times 5 times 7. Cancel the common factors so that we're left with 1 in the numerator and 5 in the denominator. Note everything in the numerator cancels because you divide the numerator by itself, hence the answer has a 1 in its numerator. When everything cancels, when all the factors in the numerator cancel, this means you're dividing the numerator by itself, hence you're left with 1 in the numerator. The same rule applies to the denominator. If everything in the denominator cancels, you're left with a 1 in the denominator. Example 7. Simplify the product. Negative 6x over 55y times negative 110y squared over 105x squared. Solution. The product of two negatives is a positive, so the result will be positive. Then we will find the prime factors of our numerators and denominators. Then cancel those common factors. And then group the numerator factors and the denominator factors together to get 2 times y in the numerator and 5 times 7 times x in the denominator. Simplifying, we have 2 times y is 4y in the numerator, and 5 times 7 times x is 35x in the denominator. Parallelograms. In this section, we are going to learn how to find the area of a parallelogram. Let's begin with the definition of a parallelogram. Recall that a quadrilateral is a polygon having 4 sides. A parallelogram is a very special type of quadrilateral. Parallelogram. A parallelogram is a quadrilateral whose opposite sides are parallel. The side on which the parallelogram rests is called its base, labeled B in the figure, and the distance from this base to the opposite side is called the height, labeled H in the figure. Note that the altitude is perpendicular to the base, meets the base at a 90-degree angle. Figure 4.8 shows a rectangle having length B and width H. Therefore, the area of the rectangle in figure 4.8 is A equals B times H, which is found by taking the product of the length and width. Take a pair of scissors and cut a triangle from the right end of the rectangle as shown in figure 4.9a. Then paste the cut triangle to the left hand as shown in figure 4.9b. The result seen in figure 4.9b is a parallelogram having base B and height h. Because we've thrown no material away in creating the parallelogram from the rectangle, the parallelogram has the same area as the original rectangle, that is, the area of the parallelogram is A equals B times h. Example 8. Find the area of the parallelogram pictured below. Solution. The area of the parallelogram is equal to the product of its base and height, that is, A equals B times h equals 6 feet times 5 over 3 feet, since the base is 6 feet and the height is 5 over 3 feet. Multiplying numerators and denominators. So think of 6 feet as being 6 over 1. So the numerators would be 6 times 5 is 30, and the denominators would be 1 times 3 is 3. 3 goes into 30 10 times, so we're left with 10 feet squared as the area of the parallelogram. Triangles. Let's turn our attention to learning how to find the area of a triangle. A triangle is a three-sided polygon. It is formed by plotting 3 points and connecting them with 3 line segments. Each of the 3 points is called a vertex of the triangle, and each of the 3 line segments is called a side of the triangle. The side on which the triangle rests is called its base, and the distance between its base and opposite vertex is called its height of altitude. The altitude is always perpendicular to the base, that is, it forms a 90-degree angle with the base. It's easily seen that a triangle has half the area of a parallelogram. The parallelogram has area equals base times height, therefore the triangle has 1/2 that area. That is, the area of the triangle is A equals 1/2 times B times h. Area of a triangle. A triangle having base B and height h has area A equals 1/2 times B times h. That is, to find the area of a triangle, take 1/2 the product of the base and height. Example 9. Find the area of the triangle pictured below with base 13 centimeters and height 6 centimeters. Solution. To find the area of the triangle, take 1/2 the product of the base and height. So 1/2 13 times 6 is equivalent to 13 times 6, which is 78 over 2. Then 78 divided by 2 is 39. And centimeter times centimeter is centimeter square. Therefore, the area of the triangle is 39 square centimeters. So let's look back for a second. On the second step where we multiplied 1/2 times 13 times 6, just think of 13 and 6 as being fractions with 1 as the denominator. Then when we multiply the numerators together, we have 1 times 13 times 6, which is 78. And in the denominators, we have 2 times 1, which is 2. Then divide 78 by 2 to get 39. So again, the area of the triangle is 39 square centimeters. Identifying the base and altitude. Sometimes it can be a bit difficult to determine the base and altitude or height of a triangle. For example, consider the triangle in figure 4.10a. Let's say we choose the bottom edge of the triangle as the base and denote its length in the variable b as shown in figure 4.10a. The altitude or height of the triangle is defined as the distance between the base of the triangle and its opposite vertex. To identify this altitude, we must first extend the base as seen in the dashed extension in figure 4.10b. Then drop a perpendicular dashed line from the opposite vertex to the extended base, as also shown in figure 4.10b. This perpendicular is the altitude or height of the triangle, and we denote its length by h. But we can go further. Any of the 3 sides of the triangle may be designated as the base of the triangle. Suppose, as shown in figure 4.11a, we identify a different side as the base, with length denoted by the variable b. The altitude to this new base will be a segment from the opposite vertex, perpendicular to the base. Its length as figure 4.11b is denoted by h. In like manner, there is a third side of the triangle that could also be used as the base. The altitude to this third side is found by dropping a perpendicular from the vertex of the triangle directly opposite from this base. This would also require extending the base. We leave this to our readers to explore. Key point. Any of the 3 sides of a triangle may be used as the base. The altitude is drawn by dropping a perpendicular from the opposite vertex to the chosen base. This sometimes requires that we extend the base. Regardless of which side we use for the base, the formula A equals base times height divided by 2 will produce the same area result.